Hello and welcome back to the AI with Maribel Lopez program. I'm always interested in talking to new and exciting leaders about what's going on in the AI space. So today I'm joined by the CEO of Vinci, Hardik Kabaria. Hardik, welcome to the program. I know that
Well,
you
thanks
have
for having me.
yeah, I know you've been talking to a lot of companies about, a lot of analysts like myself and other folks about a different aspect of AI. So I thought this would be kind of fun, but maybe to do it justice, I'll have you start by introducing yourself and what the company does. And then I have a couple of questions I wanted to ask you to get started, and we'll just have a good conversation. So tell me a little bit about Vinci and then how you decided to come into Vinci.
Yeah, I'll start with a quick intro for myself. My technical background is in physics and geometry software. So I've been building the type of tools that, mechanical engineer, electrical engineer, so hardware engineers use to design parts, understand its performance, all the way to manufacturing. So that's been my career. And I always been thinking about how can we use technology, whether it's AI or better chips, to make that life easy. When an engineer has an idea, I want to build a product like this. From that idea to parts going out in the field to then eventually parts operating in the real world. That's really the life cycle of a product in a hardware world. And that sort of applies whether you think about semiconductor components like memory, GPU, also applies to robots. It applies to consumer products like iPhone. Everything starts with an idea. I want to create something. But then that the amazing thing about hardware, it becomes physical and it stays physical and interacts with the rest of the world, right? And that's sort of the place which excites me the most. So we started this 2.5 years ago. And what specific problem are we looking at? About $4 trillion worth of hardware parts are created every year. And all of these parts are interact in the real world, governed by the laws of physics. Laws of physics are, energy balance, momentum balance. You can't really escape it. You care about it when you want to design the part. You have to care about it when the parts operate. Now, all of these analysis is done by very few limited number of engineers using the tools that have been around for a long amount of time. What we are building is foundation model for the physical world. That means we bake in this real laws of physics. This is how universe acts on every part, man-made or nature-made, so that engineers can get answers to how will my part behave? Can it be manufactured? How will it operate? What kind of heat transfer would it do? What kind of mechanical bending would it do? Would the signal integrity be preserved? And we make those answers available to these engineers across their life cycle at extremely fast pace at a higher fidelity. And that's the product we call physics intelligence layer. That's what we are building. That's what we are shipping.
Okay, perfect. And I really like this because there's a lot of discussion going on. And, for better or worse, Jensen and NVIDIA does drive a lot of discussions in the industry, right? So
Of course.
recently, his talk track since, somewhere last year was a lot about physical AI. So I think people are starting to think more about the physical domains, which are very
Yeah.
different. Now, you were starting to tee up this conversation of some of what's different about what you're doing. And when we think about what most people use with AI, it's been large language models, which are language, right? Which is, we've
Correct.
had books and website articles and Reddit and whatever, and all that has become the
Exactly.
corpus of knowledge that people leverage today. And text code, maybe images in some case when we go to the more multimodal models. But what you're talking about, I think, is very different, and the data sources are very different. So, how does something like that even get constructed? Do you have to go out and talk to different people and say, hey, I need to figure out, these physical thermal properties of something and pull them
Yeah.
into a model. I mean, there's a lot that
Yeah.
goes on in the physical dimension that's super
Okay.
different than what happens in the language dimension. So maybe you could just help me unpack that a little bit because I find this fascinating.
No, 100%. So the way I think about physics, let's start there.
Yeah.
The laws of physics were the same before humans came onto Earth, and it will be the same after humans leave the Earth. That means they are constant, they are universal. Let's make it a little bit more closer because I went sort of galactic. They are the same for every company. They are same for Apple, TSMC, Nvidia, or also one person startup trying to build a new product. So laws of physics does not really are not invented by humans. They are not governed by humans. Humans try to understand it so they can do better parts, better design, better operation of things. Now, yes, you're absolutely right. It's a different modality. So what I'm trying to take you to is that for language model, humans created corpus because we wrote down this bunch of knowledge on Reddit and whatnot, and the language models trained on it. In physics is in some ways complex, in some ways a lot more simpler because physics has existed forever. So
Okay.
what do we do with that information? So to create a model, we go back to basics. There is a heat transfer. Heat transfer is balancing heat flux or balancing energy balance. Amount of heat generated always equals amount of heat dissipated. So that laws of physics, as physicists have written down as mathematical equations, we try to teach the model those things. And we
I see.
say this that okay, it should be the same whether the heat transfer is happening on my phone or it's happening on a robotic arm, whether that phone is designed by Apple, robotic arm designed by Tesla, or it's happening on a semiconductor wafer where a bunch of dice are being manufactured. The laws of physics says energy balance is going to happen. So we are creating a model that is rooted into physics, that natively understands geometry at its modality, geometry as a shape. What is the shape of my copper wiring? What is the shape of the exterior of my phone? What is the shape of a robotic arm? What materials do I use? And then help me understand what is the heat flux? Will the heat dissipate fast enough? If not, am I going to have problems? So those type of questions it can answer. But it is rooted deeply into the physics for all kind of parts human may want to create.
So the probably the first thing to think about from a change standpoint when you're looking at AI for the physical world is in fact the physics. Are there other things that when, AI starts reasoning about the physical world, like other things we need to think about?
So yes, of course, I mean, one is the core capability and one is how humans may want to use it. And we don't try to separate the two, we try to think about it together, right? Because at the end
Okay.
of the day, this capability will be used by companies creating amazing hardware, whether it's a semiconductor company trying to build a memory or a GPU. So what I'm trying to say is that there is a raw capability. We have built a model that gives this answer zero shot. It scales like AI inference, but that raw capability is not going to be useful until it's deployed for a customer in their day-to-day life and a workflow. So now it comes to, okay, can you digest my geometry? So geometry for semiconductor or a printed circuit board is their circuitry. For a mechanical part is their shape. So now we are talking about product where our product enables the user to just bring that information and create a prompt. Prompt is here's my geometry, here's my environmental condition. I want to make this out of copper or aluminum. And then help me understand, is it going to bend? How much is it going to bend? Is it going to bend so much that it's
Mm.
going to break? That's my physics question. And we take from prompt, do the reasoning, give you the answer, and give you level of details that you can understand.
Okay. So I want to try to tee up what's the same or different about a concept that we've been looking at in the past. So, when we were moving into IoT and industrial IoT, we talked a lot about the concept of digital twinning and being able to
Mhm.
try to simulate and understand how physical products would come about, if they could come about, how they would interact. What is
Yes.
the same or different about that concept based on what you're doing today?
The concept is very similar, but the the place where AI can take us is the scale. And I'll define the scale in two ways.
Right.
One is you can make a capability available to broader and broader set of people. And instead of that capability being human bound, you can take it compute bound. And I'll make it more real. Say today,
Okay.
we go back to our original thesis that only so many high caliber humans can today help you understand physical system. So that means you are human bound. Can we convert that into compute bound? So now, as far as the prompts keep coming, we will keep
Yep.
producing an answer. And some of our customers are already there. They are able to run analysis at the speed of number of compute available to them, not restricting to number of amazing high caliber humans are clicking buttons or constructing prompts. So that's stage one of scalability. This is what AI has done in language. You can get an amazing amount of answers really fast. But digital
Yes.
twin actually has a second scalability embedded in it. Today, hardware systems are complex. You go from nanometer level copper features in your semiconductor parts to a centimeter scale parts. That's an insane amount of complexity. That's like resolving human hair on a New York City. It's
Oh,
harder
geez.
for us to imagine because we don't really imagine what happens after millimeter, but millimeter to nanometer is 6 orders of magnitude smaller. And we are producing those parts. To really create a true digital twin, we have to create a capability that allows us to query physics at that scale. Now we
At
should
the
be able
large
to
and at
produce
the tiny.
at the large and at the tiny that is 6, 7, 8, 9 orders of magnitude apart, right?
Okay.
And this is the place where AI helps. So you can create massive scalability that AI models can bring at the time of inference. So there are two scalabilities. One is making the capability accessible to more people at the compute capability. And the second is an interesting dimension that I believe you don't run into language. Can you really go to the same level of complexity of your prompt that today humans can manufacture? We are manufacturing that complexity, but if we cannot process that prompt, we haven't really achieved a true physical intelligence at the scale that world is.
That makes perfect sense. So when you think about, I guess what are some of the biggest misconceptions enterprise leaders have about applying the AI to physical systems like hardware, manufacturing, energy, all the things we were just talking about?
So AI, especially when these leaders think about generative AI, they all have experienced it and they think about, oh, if I ask a question, I may get multiple answers. So the first thing that hits them is non-determinism. The second thing they're worried about is if you make some wrong assumptions about your mechanical systems, how much heat you can transfer, right? Then you are going to either create a suboptimal product or you are going to have an issue that comes up late in your product lifecycle. In software, you can send a patch fix. In hardware, you don't have
Easily
that
fix that,
luxury.
right?
Don't have that luxury. So hardware leaders are really worried about being led into the wrong direction that may come and surface a different type of issues later. So the work we do is to say one is whether I ask a heat transfer problem, whether you ask it today or tomorrow, it should have the same answer. So our product is deterministic. We give you the same answer no matter who asks it, when they ask it, which is very different than the language model because they are more on the creative side, while physics is deterministic. The second is it's just think about it, it's easy to verify whether the energy is balanced. So that
Mm.
means our product has to live up to that standard, which is we always give you answers that are rooted into the laws of physics and are checked against those laws of physics. That means the answers provided would have the energy balance, momentum balance. And once we explain that, showcase that on benchmark, they have a different mindset about what to do with this AI product for them. versus just thinking about a language driven, a creative and force an AI model that how will that capability help them with their hardware design. So there is a creative part that could be useful, but there is also deterministic. Does it just satisfy the physics? That is extremely important for them. And this is where there is a difference. And that's the not only product features for us, but it's the explanation we do to build their confidence.
I love the way you brought that to the forefront because I think one of the challenges that we've all had as organizations as we've moved into AI was this discussion around hallucinations and do I get the same answer twice? Do I get anything near the same answer twice? It all sounds very confident, and you don't want to end up in a situation where I was trying to build a square and I ended up with a trapezoid, right? That's not
Right.
exactly the physical
That's
outcome
not a
that you
square.
wanted.
Yes.
You can't dial that back once you put it in the manufacturing line. So you really have to have that trust and confidence that is rooted in something that you can therefore say that here's what we know to be true, and we've checked it against that. So I think that's a really big difference in physical systems. It doesn't come out the same. If you're writing marketing copy, it's like, well, if it changes from this to that, it doesn't fundamentally impact the product unless it was like a full brand issue, right? So I
Yes.
think that's a huge difference. And you just started to talk a little bit about one of the other questions that I wanted to ask you about, which was, checking the validity of AI outputs and how those would impact physical products. So I think we've covered that. Uh, when you think about so I guess from your perspective, what are some of the gating issues, things that you need to overcome for this to become a reality for organizations to actually deploy? We've seen models, they've been moving pretty quickly. They're a
Mhm.
lot of them are very compute intensive, they require a lot of energy. Can you run them on premise? Do you have to run them in the cloud? There's a lot of different answers about like the how does this happen. Are the issues the same when we're looking at physics-based AI?
Yes, some of the issues are same, but I think some concerns are higher. So it's the issues are the same, but the priorities might be different. So let's look at any
Okay.
hardware engineering organization. The thing that really create is their design, the shape, whether the shape of the copper wiring or the shape of the circuitry, shape of the product, right? And they choose some materials so that those parts behave in a certain way in the real world. So that means that data privacy and security about the shape they create is something that is very high. This is the information they are going to closely guard. What it means is that let's make it tangible. A semiconductor company is not going to let somebody else see the layout of their memory or the GPU. And that means when we deploy the product, we have to deploy such that it's deployed behind that firewall. It doesn't matter where they bring it to a hyperscaler of their choice or they really put bare metal server in the data center. We deploy both ways. But security is of a paramount concern. You have to get over that, which is the same a way as saying determinism is important. Did you really check? And we go,
Yeah.
this is the place we go extra mile to say, okay, here are the equations. We checked the answer against it, and this is how close the answer is. So that means you create complete transparency of everything that happened to give you the answer. So you can, a user that is extremely capable can keep double clicking and keep going like, how well did you solve the question? I want to still know. I want to still know. So create a complete transparency. So the shape of the product that is built on the raw capability of physics intelligence for a hardware organization, I believe is very different because they have a different concerns. So that's extremely important to think through. And we have baked into it because we are trying to build this product with our customer in mind and along with them. So they tell us that you have to deploy such that we believe when we are comfortable using your product on this most secure, most sensitive flagship product we are developing. And that means it has to take this shape and form. So I would say that's the place where I've seen a significant learning that we had to do of deploying this raw capability.
That makes total sense because in the case of a lot of what you're talking about, they are highly proprietary things, right?
Yes,
You'd want to make
correct.
sure that they're the secret sauce things. Whereas when
That's the
you're
secret.
doing, say, basic LLM models across an organization, some of it's secret sauce, some of it's just basic productivity. It's not that big of a deal,
Yes.
right? So not that productivity is not a big deal, but it's not sensitive in the same way that you were just talking about it. So if I'm an organization, what are some of the biggest signals that I should be watching to see if this is working, to try to figure out if this is scalable? What do I look for?
I'll tell you how the type of conversations we are having. We start from understanding a real pain point. So somebody would say, I have a heat transfer problem, but it's not generally heat transfer problem. It comes in terms of the product performance.
Yeah.
I am trying
Okay.
to increase the power in my memory, in my semiconductor component, without violating a thermal reliability constraint. So now, see, it's in terms of product performance. I want to increase the clock speed of my CPU, my GPU. I want to pack in a lot more power, but I also want to make sure that whatever I create can still be deployed in an air-cooled environment. Or when I have my extremely high processing chips on my phone, it still can be cooled without, having a performance throttling. So that's a performance question that gets transferred into a physical problem. Right. So the signals that we look for is to understand how do we first transfer the context that they care about into the raw capability, use the raw capability to create an answer that we present to the users at different level of abstraction. Sometimes when you're just starting to design a product concept, you don't care about all the details, but you want to get directionally right. But when you're about to ship the drawings of your product to your manufacturer at sign off level, oh, you want to get all the details right. And you don't want to go to a different system. You want to get the architectural decisions extremely fast so you can iterate and you can start whiteboard and sketches. At the sign off level, you wouldn't care if your prompt runs for 7 days. Give me the right answer. That's more important. And an organization, when they are creating and adopting new tools, they care about the same tool because otherwise they are going to create one another rock in their pack. Now they have to go across 7 different tools. So as a startup, what we care about is we integrate into your workflow. How do you do things day to day? Where does your data live? Can we digest that stuff? Doesn't matter whether it's 10 gigabytes of data or 2 kilobytes of data. Digest it and help you create an answer in a meaningful way. So we care about throughput, how many queries can we process. So I think these are the things that we care about. And at the end, the answer is in the question, always. Now that's what's happening with AI. More detailed question you ask, detailed answer you're going to get. And that's true in this place as well.
That actually is really helpful. I also think it's a big change in the world. It's one of the things that analysts say all the time. It's like, oh, make sure that you understand what your question is, what you're trying to do, what goal you're trying to accomplish. And it sounds like such a simple thing to say, but in actual
Yes.
practice, it turns out that's not very simple. There's so
No.
many things you could be doing, right? And to understand the exact thing that you need to do over this course of time to make the biggest impact or even any impact, I think is one of the things a lot of organizations struggle with. But I love the fact that we're thinking more about what the question is and therefore what is the tool that we need to make that happen. And I only have a couple more questions.
Sure.
But one is, what does the end state look like if this succeeds? Are we seeing simulation tools disappear? Are we seeing certain parts of infrastructure become invisible? Like, how do I think about it as an organization? What's going to change for me?
I mean, let's start with the intent. The intent of these organizations is to create better product faster. That's the
Right.
intent. The intent is I want to create an amazing high performance memory, high performance GPU that works in this environment, and I want to ship it faster. And I want to have the 7%, 10% competitive edge. And whatever that edge is going to happen is going to happen constrained by laws of physics, right? Because you cannot really change it. So the place where it will go is okay, if I can get access to physics intelligence, physics answers at every type of scalability, it goes to can I drive the intent? The first stage of intent is going to be I want to use the answers from the physics to figure out how I want to change the design. So I get a better performance. So that's the stage we already start seeing our users unlocking. They are unlocking new insights that they didn't have access to before because they got a higher fidelity data. And they are using those insights to create better decisions for their product. But they are going to take along with them, hey, this time you created data and I created insights. Now, can you create insights? So that's analytics. Then, okay, that's the next step. Some of their partners are pulling them. You created insights. Can you also tweak the design? I'm going to do the 70, 80, 90% of the job creating a design, which is equal to writing a code. I'm going to make you do the last 10% squeeze. But that squeeze is rooted into performance. So in software, it's rooted into compilation, how the memory gets allocated. In the hardware, it's rooted into physics, how the heat flux flows through, how the data flows through, are we at the violating constraint, whatnot. So that leads to design optimization rooted into physics. And the end state is these humans are going to create an amazing, highly detailed prompt equal to what software engineers are doing today. And they're going to get a product out, which is a detailed layout with all the physical performance, completely guard band, all the scenarios performed. If you use the GPU like this, if you use the CPU like this, if the phone is in 120 Celsius weather, or it's in the AC, what kind of performance you're going to get. All of these scenarios. Now you see the value of those scenarios in hardware is extremely high because you cannot fix the hardware once it's shipped. So more analytics, more broader envelope you have considered at the time of design, the better parts you're going to ship. So our goal as a company is to make that layer available of intelligence. So hardware engineering teams will use us to create better product faster.
Okay. Uh, I'd like to close with a piece of advice. What do you think CIOs, CTOs, product designers should be doing to prepare for this shift? It's a big shift, I think.
It is a big shift, right? And I think embracing AI with the guardrails is the answer. Especially in hardware, they care about being precise. They care about, having all the scenarios considered. They care about determinism. So they should have their guardrails. But within these guardrails, they should figure out how a new capability could help them. So have a pretty high bar on the benchmarks. Create benchmarks that you can measure the tools against. Once you have the guardrails, then you'll be able to trust the new capabilities. So it's almost like separate the two parts. Don't just look at the capability, but have your independent mind of what it should do and what it shouldn't do. And if it matches that, then I think it is easier for them to build trust and confidence. So that's a longer way of saying trust but verify. But if they have a mechanism for it, I think they'll be able to use this new capability with confidence and actually take advantage of it.
Wonderful. Is there anything that I missed? Anything else you'd like to share with the audience? I mean, the whole move to AI in the physical world is actually quite exciting and challenging.
Yeah.
What are your thoughts?
I mean, it's extremely exciting. It is just like language models are kept surprising their own, teams and creators at the pace they started moving. We see that, we feel that, but more so, I'm quite excited about how the people who are using these capabilities are deriving those insights because that's the real game. Because they use that insight to do something better. So what I'm excited about is like how fast can we make this capability at the pace that world wants it and give it to them while ensuring their guardrails are satisfied. So now that's the transition I think we are in, and it's just excited to be part of it, to building it in a manner that world can build better hardware because I truly believe at the end humans interact with physical world. They interact with physical world even if they are using AI prompt. You know why? There is a data center that is processing those tokens, and if it is not cooling fast enough, you're not going to get your answer fast enough.
100%. This has been great. I so look forward to seeing what people do with your technology and how we change the physical world with AI. Hardik, thank you so much for your time and attention, and I hope you come back soon.
Yeah, thanks for having me. It was amazing to talk to you.